Chapter 9 Electrolyte Solutions Section 9.6 Sort in and sort out effects. The sort in and sort out effects are referring to adding a salt into the aqueous solution of a chemical may increase or decrease its solubility. Here's an example. If we add the sodium nitrate salt into the saturated aqueous solution of magnesium fluoride, this sodium plus can help stabilize the chloride. Nitrate can help stabilize the magnesium cation in the aqueous solution. And therefore, adding sodium nitrate may increase the solubility of magnesium chloride in water. And this is one of the examples of sort-in. Now let's look at the solubility equation for magnesium fluoride. On the left-hand side, we have magnesium fluoride in the solid phase. Right-hand side, we have magnesium cation and fluoride cation. At the room temperature, we have Ksp equals 6.4 times 10 to the power of negative 9. And we have learned in the previous section, Ksp is gamma to the power of 3 times 4 times the concentration of dissolved magnesium fluoride over C0 to the power of 3. So first, this gamma is the mean ionic activity coefficient. The reason we have 4 here is because the concentration of fluoride is 2 times the concentration of magnesium. And we need to have the concentration of fluoride squared. So that's why you see a 4 here. And over here we have the concentration of magnesium fluoride over C0. This is simply to remove the unit. And we are assuming the standard state is 1 molar. Now at the same temperature, room temperature, Ksp is a constant. That's not going to change. However, if you look at this equation, you can see, well, the concentration of magnesium fluoride is inversely proportional to gamma. So you can see if this times this is a constant, then the concentration of magnesium fluoride is higher when you have a smaller gamma. The concentration of magnesium fluoride is lower if you have larger gamma. And also, mathematically, we can rewrite this equation C, the concentration of magnesium fluoride over C0 is simply the cubic root of Ksp over 4 on top, and then divided by gamma plus minus. Gamma plus minus is the mean ionic activity coefficient. So if we can lower this activity coefficient, we can increase the concentration of magnesium fluoride in water, and that means we can increase the solubility of magnesium fluoride. But how can we reduce this gamma? Well, it's pretty simple. We can increase the ionic strength of the aqueous solution. Here's an example. If we add 0.1 molar sodium nitrate into this aqueous solution of magnesium fluoride, the ionic strength is increased. Why? Because now we have 2 different salts, and the ionic strength of sodium nitrate is this much. This is the molarity over 2, and then we have sodium nitrate over here. Together it's 0.1 molar from sodium nitrate. What about the ionic strength from magnesium fluoride? Well, it's just the concentration of magnesium fluoride is pretty low. So even if the dissolution of magnesium fluoride contribute to the ionic strength, that contribution is much smaller than 0.1 molar. So we're going to just use 0.1 molar. Now we just use this ionic strength. This is a approximate value. We use this to compute the mean ionic activity coefficient for the solution after the addition of 0.1 molar sodium nitrate. So we're going to use this equation. This is the Debye-Hurkle equation for computing the mean ionic activity coefficient. We get this gamma equals 0.69. And now if gamma is 0.69, we plug in this value into this equation. And again, this equation comes from this equation. And then we can compute the concentration of magnesium fluoride, which is 0.0017 molar. This is higher than the previously calculated 0.00117 molar with a zero ionic strength. It's also greater than the value over here, 0.00136, even after we consider the ionic strengths that come from magnesium fluoride. So this is so-called salt-in effect. All right. After we add sodium nitrate into the saturated solution of magnesium fluoride, we can further enhance the solubility of magnesium fluoride. What's the physical reason behind this? It's very simple. Again, sodium plus helps stabilize fluorine minus. Nitrate minus helps stabilize magnesium 2 plus in the aqueous solution. And therefore, by adding a different salt, we can further stabilize the magnesium cation and fluoride ion in the aqueous solution, and then in turn we increase its solubility. But adding too much sodium nitrate into this magnesium fluoride solution may sometimes decrease the solubility of magnesium fluoride, and this phenomenon is called salt out. Well, in this case, if we add too much sodium nitrate, this sodium plus and nitrate ions may attract too many water molecules, most of the water molecules, and consequently deprive the opportunities of the magnesium cation and fluoride anion of being fully solvated. And then we can dissolve less magnesium 2 plus and fluorine minus ions in water. Well, only because we have fewer water molecules available to solvate these two ions. There's another way to reduce the solubility of magnesium fluoride, which is to somehow add another chemical that either contains magnesium cation or fluoride. This is actually due to the Le Chatelier principle. Now let's look at one example. If we add 0.01 molar sodium fluoride into a saturated magnesium fluoride solution, you can see we're adding new fluoride into this solution. Magnesium fluoride precipitates out. Here's the reason. For convenience, let's just assume the mean activity coefficient is just constant 1 so that we don't have to worry about this. We'll just analyze this sort out effect semi-quantitatively. So if this is 1, we can easily compute the solubility of magnesium fluoride. It's 0.00117 molar. Alright, using this equation, we solve this equation, we get 0.00117 molar. Now if we add 0.01 molar sodium fluoride into this aqueous solution, we have a different concentration for fluoride. Okay, it's 0.01 from this sodium fluoride. And I'm using a variable x here. X is the concentration of dissolved magnesium cation. Alright, so if you have X as the concentration of magnesium cation, then 2X is the concentration of fluoride that comes from magnesium fluoride. Right, there's a ratio between magnesium and fluorine in magnesium fluoride, which is 1:2 ratio. So we have this. Again, X is just the numerical value of the concentration of the dissolved MgF2, or the concentration of the magnesium cation. Now we have a different equation. So X is the concentration of the magnesium cation, but then fluoride is 2X and then plus 0.01. That comes from sodium fluoride. So we have a new equation over here. This is a third order polynomial equation, but we can still solve this. We get a different concentration right here, and this concentration is actually much smaller than this concentration. So that means by adding sodium fluoride, we can decrease the solubility of magnesium fluoride. Again, we can use the Le Chatelier principle to make the same prediction. Now let's look at another numerical example problem, 9.6.1. This time we're going to add 0.01 molar magnesium nitrate into the saturated magnesium fluoride solution. So again, we're adding more magnesium 2 plus. That means we will be able to see magnesium fluoride precipitate out of the solution based on the Le Chatelier principle. Now let's look at the calculations. Again, for convenience, we're going to just assume the mean activity coefficient is constant 1 so that we don't have to worry too much about computing this. The solubility of magnesium fluoride again is 0.00117, just the same calculation here. And now we add 0.01 molar magnesium nitrate into this magnesium fluoride solution. So now you can see the concentration of the magnesium cation is set to X plus 0.01 molar. 0.01 over here comes from magnesium nitrate. X is from the dissolution of the magnesium fluoride. So if X molar magnesium fluoride is dissolved, we have 2X as the concentration of fluoride. So that's why we see 2X here, 2X squared. And over here, X plus 0.01, this is magnesium 2 plus, and this is fluoride concentration. Now we solve this equation, and we get X equals 0.00039, which is also much smaller than the original value. It's roughly only 1/3 of the original value. Again, by adding magnesium nitrate, we introduce additional magnesium cations into the solution. That reduces the solubility of magnesium fluoride. We can use the calculation to see this statement is true, and also we can simply use the Le Chatelier's principle. By adding additional magnesium 2 plus, this solution should move in a direction to reduce magnesium 2 plus, right? So the system responds in a way to cancel out the external forces or external effects. So that way we have a reduced solubility of magnesium fluoride. Now let's switch the topic a little bit. We can also add a large amount of salt to precipitate protein out of its aqueous solution, because if you think about this, protein molecules, they have hydrophobic functional groups. They have hydrophilic regions. So hydrophilic regions can be solvated by water molecules, and hydrophobic regions can attract each other due to the van der Waals interaction or dispersion interaction. But now if you add a very large amount of salt into the aqueous solution of protein, then, well, again, the large number of salt ions may attract too many water molecules away from protein, and that's going to deprive the opportunities of the hydrophilic regions of the protein from being fully solvated. And then the protein molecules will start to coagulate. That means change to a solid or even semi-solid state due to the attraction between their hydrophobic parts via dispersion attraction. So here, adding salt reduces the solubility of the protein in water, and you can try this in the kitchen. You add a very large amount of table salt into milk, and we can observe the salt out phenomenon.